Hello.
Good evening, sir.
Hello. Good evening. Am I audible?
Yeah, you are audible.
Okay. Good evening and welcome all for this session for the NPTEL course Advanced Thermodynamics and Combustion. This is our third session, and in this session we will be focusing on the content of week 3. In week 3, the topics we discussed are mostly entropy and exergy. Okay. So if you have any doubt in the lectures or in the previous sessions or in the previous lectures, that you can ask, and then we can proceed for some examples. And you can also ask the questions in between the session. Okay. Okay. So if you have any, if you have no doubt, then probably we can start with the questions. Okay. So there is a note. It is saying that we have to use T naught and P naught to denote the dead state temperature and pressure respectively. Okay, fine. When we'll be solving the problems related to exergy, we know that there is something called dead state. Okay. What is dead state? That we will discuss in the upcoming questions. But for the time being, let's start with question number 1. It is fill in the blank. So it is saying that a quasi-equilibrium process, which is governed by sorry. Okay, sorry. So it is saying a quasi-equilibrium process, which is governed by PV to the power n is equal to some constant. That is called what we call such type of processes. Very easy. We call them polytropic processes, right? So some initial questions will be, some easy revision type of questions. So this type of process, we call it polytropic process. Okay. So I don't think that there can be any doubt in this question. If it is there, then you can ask, or we can move to the next question, question number 2. So it is a multiple choice type of question. It is saying that for an ideal gas, what is happening? It is saying that for an ideal gas which is undergoing an isentropic process, ideal gas and isentropic, two keywords. Okay, which of the following relations correctly links temperature and pressure? So which of them is correct?
T2 by T1 is equal to P2 by P1 whole power K minus 1 by K.
Okay, so part B, right?
Yes, yes.
And if we are asked to derive that for an ideal gas and isentropic process, the relation is like that, then how should we proceed? We should start with TDS relation, okay? Because the TDS relation,
Yes.
for example, TDS is equal to du plus PdV. We discussed in the previous session that this is valid for all the processes, regardless of the process being reversible or irreversible, because all the variables involved are point functions. None of them are path function. Okay, so it is valid for both reversible and irreversible process. Okay. Now it is saying that it is an ideal gas. Okay. So for ideal gas, we can write du is equal to Cv dt. Okay. This is for ideal gas. And it is saying isentropic process. So that means ds is equal to 0 because it is isentropic process. Okay, so this TDS relation basically becomes 0 is equal to, because ds is equal to 0, 0 equal to Cv dt plus PdV, right? And from this relation, we can get this relation. Okay, we just need to do some algebraic manipulations. Okay. Now, coming to the next question, question number 3. There are some statements and we have to tell whether they are true or false. So first statement, it says that in the energy rate balance for steady flow devices such as turbine and compressors, the heat transfer term Q dot CV. Okay, so this is heat transfer term. This is basically time rate of heat transfer for the control volume. This is frequently set to 0 when we are working with turbines and compressors. Okay, so usually this term we neglect. Okay, and it is saying that we do this because this term is small related to other energy transfer across the system boundaries. So we have to tell that whether this is true or false.
Yeah, it is true, sir.
It is true, right? Why? Because this
Yes,
term
sir.
is relatively small. Okay, so turbine we usually assume that it is, there are no heat losses, and same thing for compressor. Okay, and usually it is in many questions it is given that assume isentropic turbine, right? So when we say isentropic for these turbines or compressor, we basically mean that it is reversible and adiabatic. Okay, but in the previous sessions, okay, we will come to that point. So in many questions we encounter this term, right? Assume isentropic turbine or isentropic compressor. So we usually assume that this is reversible adiabatic. Now there is another part. It is saying that negligible heat transfer. So that means if dq, this thing is 0, which we are assuming in this type of devices, like it is given in the first part that we make this term 0. Okay, so if we are making this term 0, or let us say dq, it is 0. So does that mean that device is reversible?
Not exactly. It could be reversible or irreversible depending on whether it is isentropic or not.
Right, correct. So the statement is false, right?
Yes.
Right. So as you said, this is implies reversible. Sorry, reversible only if this is isentropic, or it will be irreversible if it is not isentropic. Okay, so this statement is actually false. Okay, so both things should be there, right? It should be isentropic and adiabatic, then only it will be reversible. If only dq is equal to 0 and isentropic is this isentropic
It could be
information is not
isentropic, could not be isentropic,
yes,
depending on.
right. So in the ideal case, it should be adiabatic and isentropic. But in the actual case, in the actual turbines and compressors, we know it is not isentropic. The exit entropy is higher than the entrance entropy at the entrance, right?
Yes.
Okay. Just give me 1 second. I think there should be some spaces between the pages. Okay. Okay, we will insert some pages, no problem. So question number 4, it is saying that using internally reversible work integral. So we know this formula, right? We have discussed this formula has been discussed in the lecture, right? we have to explain mathematically and physically why a liquid pump requires significantly smaller work input per unit mass compared to a gas compressor when the pressure rise is same, okay, operating across the exact same pressure difference. Okay, so if the pressure rise is same, we have a pump and we have a compressor, and the pressure is same for both compressor and pump, then pump requires less work input. Why so?
Since the state of the medium, working medium is different, there will be like in shown in the diagrams, liquid plus vapor phase, there will be a different work input required for pressure rise. Is it?
Mhm. And
Is it the
if we
specific
simply
volume is? Yeah,
right,
if the specific volume, is it because of the specific volume?
right. So for gas compressor, let us say we have a gas and there is no like liquid. Okay, so for gas we have very high specific volume, right? And
So
for
is it like
liquids,
due to compressibility factor?
even if you don't invoke the compressibility factor, this V is high, right? Because the formula is simply V dP, right?
Yeah. Mm-hmm.
Okay, and dP
Yeah.
is same. Okay, this dP, this is same. So only variable left is this V term, right? So this V
Yeah.
is high
Yeah.
for gas. Okay,
Yeah, sure.
and so okay. Question number 5. It says that a steady flow reciprocating compressor compresses air from 1 bar 290 Kelvin to 4 bar. The process follows a polytropic path with an index n equal to 1.3. Assuming air behaves as an ideal gas, and this gas constant is given, it is asking us to calculate the internally reversible work transfer per unit mass in kilojoule per kg, and also the exact temperature. So it is a polytropic process. So for polytropic process, we can write PV to the power n is equal to some constant, and here n is equal to 1.3. Okay. And for polytropic processes, we know what is the work input. Per unit mass I am writing, okay. This is minus nr divided by n minus 1 T2 minus T1, right? Correct?
Yes, sir.
For polytropic process. Okay. So T1 given, right? What is given? T1 is given. T1 is 293, and P1 it is
P1
1
4
bar.
bar. Is it?
And P2 it is 4 bar, and we don't have T2, right? So T2 we
Yes.
can calculate, right? T2 we can calculate from this polytropic relation. Where is the polytropic relation? So T2 by T1 is P2 by P1, this formula, right? So from here we can calculate T2. So T2 will be T1 times P2 by P1 raised to power
K minus 1 by K.
by n, right? And T1 is 293. 4 is to the power
0.3 by 1.
1.3. Okay, so maybe can just get this thing. 293 times 4 raised to power
403.
0.3. Okay, 1.3.
403.46.
Okay, 403.46 Kelvin. So we have got T2. Okay, and what else we need? Okay, we got everything, right? T2 minus T1, we just need to substitute in the formula. So I think you can substitute and get it, right? So it was asking this work done we can calculate from this, and T2 is the exit pressure, right? Exit temperature, sorry.
Yes, yes. 136.8 minus 136.8.
Okay, I don't have the values I have to calculate, but anyways, so this is a simple question, right? You just need to substitute it.
Yes, yes.
Okay, so question number 6, it is saying the isentropic efficiency of a turbine is defined as the ratio of. So we have some options, H1 minus H2. Okay, so 1 is basically inlet and 2 is outlet, actual one. And 2S, so if you see any S, that means it is
Reversible. Isentropic.
outlet for reversible one. Reversible outlet.
Yes.
Isentropic. Okay, so question number 6. So there are some options. So which one of them should be correct?
H1
Option B.
minus H2 by H1 minus H2S.
Option B, right?
Yes.
Yeah. Sir, here one doubt.
Mhm.
Actually, this isentropic efficiency we are defining, and
Mhm.
exergetic efficiency also we are defining.
Which efficiency?
Actually, exergetic, that second law efficiency, second law efficiency.
Mhm.
So, are they? What is the difference between that, sir? Are you explaining in this lecture that?
Second law, in the second law efficiency, what we calculate is we calculate the actual work done that we have got divided by the work done that we could have got in the case of reversible one, right? And
Yes.
and
That
in the
is so. That's
isentropic efficiency also we are calculating the actual work done divided by the work done that we could have got in the reversible case. Okay, so yes, they are same, but the term, I mean, this isentropic efficiency we usually use for turbine and compressors, but essentially they are same, right? Because the concept is same, right? The actual one, the actual work that we are getting divided by the work that we could have got in the case of reversible one, right?
okay. So both are same only. That's what you are saying.
Both are same only, right? The fundamental concept underlying the both of these efficiencies is same, right? Both are coming from the second law, right? We can also prove that, okay? Okay. So coming to the next question. And you can try to prove it yourself, okay? That isentropic efficiency and the second law efficiency, they are same, okay? Question number 7, it is saying that for an ideal gas which is undergoing an internally reversible isothermal process. So for isothermal process, we know n is equal to 1 for the polytropic equation. The specific work is calculated using the polynomial expression, this polynomial expression. So we have to tell that whether it is true or false. Is it true or? Hello? Is it true? Obviously not true, right? n is equal to 1, and in the denominator you are
yeah,
getting
n is
n
equal
minus
to
1.
1, it will be
Yes.
log of
So,
P2 by P1.
whatever the formula is, but I mean, it is very obvious that if you are having n minus 1 in the denominator, then this should not be valid for n is equal to 1 type of processes, right?
Yes.
So this is false. Now, next question. The reversible maximum specific work for a liquid pump. Okay. Assuming incompressible fluid simplifies to the expression. So we had the expression for work done previously, right? When we were discussing this compressor and pumps. So what we had integral of V dP, okay,
V dP.
from like that, right? So if
Yes.
this incompressible fluid, for the incompressible fluid, this specific volume is essentially
It will
constant, okay? So this will be
Yes.
specific
Integral
volume
dP.
integral of dP from 0.1 to 2. So this will simply become P2 minus
Minus V
P1.
of P2 minus P1.
So this is the expression. Okay. Now question number 9. Sorry. It is saying that a steam nozzle operates at steady state with inlet condition of 10 bar and 320 degrees Celsius. And an inlet velocity of 30 meter per second. The exit pressure is 3 bar. Given the actual exit enthalpy, H2 is given, and the inlet enthalpy, it is also given. And the isentropic exit enthalpy, this is also given. We have to calculate the nozzle isentropic efficiency. So this is quite easy, right? We can calculate
Yes,
it.
yes.
So
H1 minus.
Whenever we
So
see this term, for the
so for the examination, whether we have to take this steam tables or other property tables.
I don't think
such.
no. I don't think that you need property table or any paper or any notes for the exam. I don't think so, because in the most of the questions
So
where we need this
they
value,
will be
this must
providing.
be given.
Whether they will be
Yeah, they
providing.
must be providing.
Okay.
Yes, I'm not sure, but they should be providing, right? Because practically it is very difficult that to check all the students what steam table they are carrying. They are not carrying any notes or something like that, right? So in the most of the questions it is already provided, but I'm not sure for this particular case. So I think before the exam they will be sending some instructions, so it should be clear. Okay, for this nozzle efficiency. So what will be the nozzle efficiency?
We had the formulas.
We
wrote the formula just now.
We wrote the formula for the turbine.
Yeah, nozzle, right?
This is nozzle.
So it will be U2 square by 2 minus H divided by U2 square by 2 for actual by reversible.
Correct. Whenever we see this term efficiency, I mean, so by efficiency we mean what our goal is, okay, and what actually we are getting divided by what actually we could have got, okay. So what actually we are getting in case of nozzle, so that will be increase in kinetic energy, right? The purpose of nozzle, any nozzle, is to increase the kinetic energy, okay. So
Kinetic
we will
energy.
calculate what is the actual amount of increase in kinetic energy, that we will calculate first, okay, and we will divide that by what could have been the amount of kinetic energy increase if the process was isentropic, okay, and we will just take the ratio, okay. So it is simply a energy balance, okay. If we write the energy balance equation, this is enthalpy at inlet plus kinetic energy at inlet. This should be equal to Enthalpy at
outlet
outlet
plus
divided
kinetic energy.
plus kinetic energy at the outlet. Okay. So you can calculate increase in kinetic energy, the actual one. Okay. So what we have inlet velocity, and we don't have the outlet velocity, right? So anyways, but we can calculate the increase in this kinetic energy. Okay. So increase in kinetic energy we can get from this equation. Actual change in kinetic energy will be this
270.5.
okay, whatever it is. So this should be H1 minus H2, right?
Minus
And isentropic increase
Ah.
would have been H1 minus H2S,
Okay.
right? And we will just divide these two things. Okay. Is it correct? I think this would be the procedure, right? Right? So
No,
we
but
can
there will
calculate
be inlet velocity also, right?
inlet.
Velocity.
No, inlet velocity we have, no, this inlet velocity,
Yeah.
but I don't think we need the inlet velocity because we have the enthalpies. Okay. We want to calculate the outlet kinetic energy in the
Yes,
case
we
of
need to calculate outlet kinetic energy. Is it like difference between the inlet and outlet, or the outlet kinetic energy? We are actually
no, outlet kinetic energy.
yeah.
So we need to calculate the outlet kinetic energy. Sorry. So the efficiency, this should be for nozzle, it should be outlet kinetic energy, that is V2 square by 2 actual one divided by V2 square by 2 in the isentropic case.
So
Okay.
for this delta KE, we can just remove U1 square by 2 on both sides.
Yes.
Numerator and denominator.
Right. So we have all the, enthalpies at inlet, outlet, both for both cases, isentropic and non-isentropic, and we have inlet velocity, so you can calculate. Okay. We will not need this temperature and pressure values.
Yes.
If we didn't had these values, enthalpy values, and we had the steam tables, then we would have required these pressure and temperature values to check these enthalpy values from the steam table. Okay, so we are asking that whether we need to carry. Okay, so if these enthalpy values were not given in the question, then we would have required the steam tables, but here it is given in the question. So questions should be of this type. So this is my guess, but you should read the instructions before the exam. Okay. So question number 10, it is saying that exergy is defined as the maximum theoretical work from a system. And we have to explain what is dead state in the context of exergy. And it is also asking to specify thermomechanical conditions required for system to reach it. So when we talk about exergy, we talk about dead state. So what that dead state is? Okay, so for dead state, I have taken this content from book Sinzel Bowles. So we will just read it, and I think everything should be clear. Okay, it is just theory. So in exergy analysis, the initial state is specified. Okay, right? Like the state of system will be given. This is the temperature, this is the pressure, whatever variables we require to define a state of the system, those will be given. Okay, so that is not a variable, so those are given, right? Why it is given? Because what will be asked? It will be asked calculate the exergy of this particular system. So whenever we say this particular system, then we should have a defined state. Okay, so state will be already defined, so that is not a variable. Okay, now if the state is changed, okay, so we are going from state 1 to another state, so then we can have some work interactions. So the work output will be maximum when the processes between the two specified states is executed in reversible manner, right? So this we have already discussed, right? If we want to calculate the work output, then work output is maximum if the process is reversible. Fine. Therefore, all the irreversibilities are disregarded in determining the work potential. Okay, so when we say work potential, that means the maximum work that can be extracted from a particular system. Okay, so if you want to extract the maximum work, then the processes which are involved, those processes should be reversible. So irreversibilities should not be there. Irreversibilities should be discarded. Finally, the system must be in the dead state at the end of process to maximize the work output. Okay, fine. What the dead state is, that we still have not defined, but dead state means now system is dead. So dead means something which is dead. I mean that cannot produce any work. Okay.
So is it like in equilibrium, sir?
Equilibrium with the environment, actually. Okay, so if it is in equilibrium with the environment, then there is, no work potential left. Because for work, there should be some potential difference, right?
Yes, yes.
So the system is said to be in dead state. Now the definition of dead state is coming. The system is said to be in dead state when it is in the thermodynamic equilibrium with the environment it is put. Okay, it should be in the thermal equilibrium with the environment in which it is kept. Okay, so this is the meaning of dead state. At the dead state, a system is at the temperature and pressure of its environment. Okay, so temperature is same with the environment, that means it is in thermal equilibrium. Pressure is same, that means it is in mechanical equilibrium. And it has no kinetic or potential energy relative to environment. Okay, so in the reference frame of environment, system should be stationary. Okay, so zero velocity and zero elevation from the reference point. Okay, so zero elevations means there is no kinetic energy, there is no potential energy, and zero velocity means there is no kinetic energy, and it does not react with the environment. So that means it is in the chemical equilibrium as well. So when all these equilibriums are there, then we will say, okay, it is in the thermodynamic equilibrium with the environment. So this thermodynamic equilibrium itself is sufficient. Okay. Also, there are no unbalanced magnetic forces, electrical forces, or surface tension effects between system and surrounding. Okay, so basically it is equilibrium from all the aspects. Okay, electromagnetism, from this, thermodynamic aspect. So there is no potential difference, any type of potential difference, neither gravitational potential difference, neither this electrodynamic potential. Okay. So we have encountered few terms like surrounding, system and surrounding we have already discussed, immediate surrounding and its environment. So the surrounding is everything outside the system boundary. Okay, so we have a universe, big universe, and within the universe we have our system. So everything outside the system is surrounding. Okay, so this we already know. The immediate surrounding refer to the position, to the portion of the surrounding which is affected by the process or the system. Okay, and the environment is that portion of immediate surrounding whose properties are not affected by the process at any point. Okay, sorry. Environment is basically region beyond the immediate surrounding. Okay, so we have this system, and outside the system we have its immediate surrounding. Okay, for example, if you consider that this is a hot cake, then just around this system, this is its immediate surrounding. Okay, This is affected by the system. But if you go little far from this, then you will get, I mean, if you have a big room and you have kept your hot cake in one corner, then most probably another corner will not be affected. Okay, so this outer region, this is our environment. And the whole thing, which is even beyond, starting just from the system boundary and including everything just beyond this system boundary, it is universe. Okay, our surrounding. Okay, this is our surrounding. So the surrounding plus system makes the universe. Anyways, so any reversibility during a process occur within the system and its immediate surrounding. Environment is free from any irreversibility. Okay. So wherever the process is being occurred, irreversibility can be within the system. It can be just outside the system, which is immediate surrounding. But environment, which is little beyond these immediate surrounding, that is free of any irreversibility. Okay, when the system is in thermodynamic equilibrium with the environment, then we say that system is in the dead state. Okay, so this is the meaning of dead state. So this is what was asked in the previous question. Okay.
Yes, sir.
Okay. Now question number 11, it says, which of the following statements accurately differentiates energy from exergy? We know that energy and exergy, they are not same, they are different. Option A says that energy is destroyed by irreversibilities, but exergy is a conserved property. We know this is not right. Energy is conserved quantity, right? Irreversibilities will not destroy the energy. Irreversibilities may change the form of energy. It can be changed from, a higher grade energy to lower grade energy because of irreversibilities, but it will not be destroyed. Exergy is not a conserved quantity, by the way, right? Option B is saying both energy and exergy are conserved properties, but exergy only applies to open system. So again, this is not correct. Exergy, first of all, it is not conserved, and exergy does not only applies to the open system, it is also for closed system. Option C is saying that energy is conserved property while exergy is destroyed by irreversibilities within the system. So this is the correct one, right? Exergy is destroyed because of irreversibilities within the system. Last option says that exergy and energy are identical properties, but are measured from different reference temperatures. So again, this is not correct, right? So option C is the correct one. Okay. Now coming to the next question. Question number 12, it says the decrease in exergy principle states that for an isolated system, the only processes that can occur are those for which exergy of overall system decreases. So is it true or false?
True.
True, right? In the previous session, we have discussed that for an isolated system, only those processes are possible for which entropy of the overall system increases. Okay, and this is just another version in terms of exergy, and both are actually just different language. Okay, so exergy of an isolated system will decrease and entropy will increase. So this is true.
Yes.
Okay, if there are irreversibilities, then exergy will be reduced. Now coming to the next question. Question number 13. The specific exergy E of a closed system accounts for internal energy, right? Boundary work, entropy, kinetic and potential energy changes relative to the environment. And the expression is E. E is for entropy, okay? So just be careful about the notation, right? because many times we use this E for, energy, right? Specific energy or any form of energy. But here it is used for specific exergy. So this specific exergy is U minus U naught. U is basically the internal energy per unit mass of the system. Sorry, U is the internal energy per unit mass of the system, and U naught is the internal energy per unit mass of the system when the system will be in the dead state. Okay. At the very beginning of the session, we have said that this naught, T naught, P naught, all these naught will basically means dead state. Okay. So U naught means the internal energy per unit mass of the system when the system will be at the dead state. So the expression is E is equal to U minus U naught plus P minus, plus P naught times V minus V naught plus, minus T naught times S minus S naught. So plus one more term. So what is that term? One is internal energy. Another is related to boundary work, right? So this is for internal energy. This is for boundary work. And this is for entropy. And there will be one more term that will be for kinetic and potential energies. Okay. So this will be
Yes.
kinetic plus potential energy. So V square by 2 plus G and Z. Z means the height from the reference level. Okay. So this will be the term which should go there. Okay. Now question number 14. In the closed system exergy balance equation. So here 2, 1, all these subscripts means states, final state and the initial state. And there is a few more subscripts, right? So for the closed system exergy balance equation, E2 minus E1 is equal to EQ minus EW minus ED. Define the term ED. We have to tell what the term ED is. Okay. EQ basically means exergy associated with heat. EW basically means exergy associated with work minus ED. So what is this another term ED?
Is it disintegrated exergy due to the irreversibility?
Exactly, correct. So this ED here is exergy destroyed due to irreversibilities. Okay. So if we are asked to calculate the exergy destroyed in any process, then we can easily calculate. How can we easily calculate? From this balance equation. We can calculate the exergy at the final state. How will we calculate the exergy at the final state? From this particular equation, right? How will we calculate the exergy at the initial state? Again, from this particular equation, right? We have the exergy at final and initial state. We will take the difference. So that will be the exergy, change in the exergy. Okay. We can calculate the exergy associated with heat. What is the exergy associated with heat? That I think that we might have studied in the lecture. I'm not sure. Okay. And exergy associated work is basically work itself. Okay. Exergy associated with work is work itself. Minus this ED. So this ED is exergy destroyed. Okay. So from this balance equation, we can calculate how much the exergy is destroyed. And how much exergy is destroyed, that is basically a measure of the irreversibilities. Okay. So more is the this exergy destroyed. That means more is the exergy, sorry, irreversibilities. Okay. So this is very important. Okay. So irreversibilities are measured not by change in exergy. Okay. Because it can happen that system is going from state A to state B and exergy is being reduced. But reduction in exergy, that does not mean that process is irreversible. Okay. Irreversibility means there should be exergy destruction, right? So we will have to calculate ED. So if ED is positive, that means it is irreversible. If it is 0, that means it is the process is irreversible one. Okay.
It could be never be negative, right, sir?
It can be negative. It can be negative. Sorry.
Cannot be.
Can this term ever be negative in a real thermodynamic process? It is just opposite
No,
of.
impossible.
It is just yes. It is just opposite of entropy. Actually, the ED
Yes,
and this exergy destroyed, this thing is equal to T naught times entropy generation. Okay. T naught is the temperature of the dead state or the environment, and entropy generation, you know, right? We have already discussed. So T naught, can temperature be negative? No, temperature is always positive, right?
yes.
Temperature is always positive. It is in Kelvin. And entropy is only generated, okay, in irreversible process. If it is not generated, then it is reversible process.
Zero.
Okay. So this will be either positive or 0. It will never be negative. Okay. Since temperature is positive, this entropy generation is either 0 or positive. So this entropy exergy destroyed, which is basically the T naught times that this entropy generation, this term will have to be positive. Okay. And second law of thermodynamics says, actually this is the second law of thermodynamics, right? Another statement of second law of thermodynamics. Right?
Yes, sir.
So we had to justify our answer using the second law of thermodynamics that we have already done. Okay. Coming to the next question. It is saying that an internal combustion engine cylinder contains gaseous combustion products at 7 bar. Okay. Just before the exhaust valve opens, the specific properties relative to the dead state, and the properties of dead states are given, T naught is given, P naught is given, are calculated as. Just before the exhaust valve opens, the specific properties related to dead state are calculated like this. U naught, it is given. S minus S naught, it is also given. If the flow work term P naught times V minus V naught is calculated like this, we have to calculate the specific exergy of gas in kilojoule per Kelvin. And it is saying that we have to neglect this kinetic and potential energy. So again, this is very, I mean, just not a question, it is just. We have already discussed, right? Exergy is this. There is some internal energy term, there is some boundary work term, entropy term, and kinetic and potential energy term. It is saying that we have to neglect the kinetic energy and potential energy, and these things have already been calculated. So we don't need to do anything, right? So nothing is left to calculate for us. So questions are very easy in today's session, but the concepts are important, okay? Kinetic and potential energy changes we have to neglect, right? So this thing is already given, this thing is already given. And what else? This thing is already given, T naught is already given. We have
E
to
naught is
calculate
given.
E. We can calculate E, so no problem. Okay, we just need to add all these values, right? Okay, for a steady state control volume, the specific flow exergy differs from the specific exergy of a closed system E, because it replaces internal energy U with which property to account for the flow work. Hello?
Yes, sir. Yes, sir.
It's enthalpy.
Enthalpy, right? In open systems, we have Q minus W is equal to U, right? Closed system. For open system, we have Q minus W is equal to H, right? This is for energy balance. And similarly for, exergy also, this U is replaced by H for open systems. Enthalpy. Why? Because open systems involves the flow work. What is flow work? Actually, how much is the flow work?
There
Flow
will
work
be work
is
mass
PV,
interaction also.
right? Per unit mass, if you write, it will be simply PV, specific volume, right? Because mass which is crossing the boundaries, that carries some flow work, and that flow work is basically P times the specific volume. Okay, so the enthalpy has internal energy plus this flow work, so both are bundled within the enthalpy. Okay, coming to question 17, it is saying that exergy rate balance for a control volume. The exergy transfer accompanying heat transfer Qj at boundary temperature is Tj is given directly by Qj without any temperature scaling factor. So is it correct? Now it is important, because somewhere I said that what I said. Yes, here we said that exergy change in any process can be calculated using this equation, or actually exergy destroyed can be calculated using this equation, because we can calculate the exergy at initial state and the final state. We can calculate the exergy associated with the heat and exergy associated with the work. Exergy associated with the work is work itself, but exergy associated with heat, that we should calculate, and how that is calculated, that is asking in this question. It is saying that exergy transfer accompanying heat Qj at boundary temperature Tj, it is simply Qj. Is it correct? Because what I said that exergy associated with work, this is work itself. Okay, but exergy associated with Q, is that Q itself? It is saying that it is given directly by Qj. Is it correct?
No, not correct.
Not correct. Why not correct?
It's not.
That's 1 minus T0 by Tj to be considered.
Right, because if there is some heat at temperature Tj, okay, so if we have some heat at temperature Tj, some Qj heat at temperature Tj, and environment temperature is T naught. Okay, then we can run a heat engine between this particular temperature Tj and T naught, right? And we can calculate the this. We can get some more work, right? So how much work we can get? That work will be equal to this Q and 1 minus Tj by T naught. Okay. And one important thing you should also remember is that, so if this is a body, some finite body, let us say it is an iron ball, a hot iron ball, it has some temperature, then this Tj will be reducing gradually. Okay. So we will have to, we cannot use this directly. Instead, we will have to use the integration, right? Correct?
Yes. Yes.
Then there's some logarithmics, some log function will come into the picture. But anyways, the important thing is that we need to calculate the work associated, and the work itself is, directly
Is it
the exergy.
T0 by Tj, or I think it is T0 by
Sorry.
Tj, right?
Sorry. Can you please repeat?
I think it is T0 by Tj, no, sir? You written Tj by T0. Yes.
Sorry. Oh, thank you. Correct. Okay. So the scaling factor is there. So that scaling factor is how much? So that scaling factor is actually the Carnot one. Carnot factor, we can say. It is 1 minus T naught by Tj. So this statement is actually false. Okay. Now coming to the next question. Question number 18. It is saying that exergy destruction rate ED is directly proportional to the entropy production rate through the relation. We have already discussed this, right? What is this? This is dead state temperature or the environment temperature times exergy generation. So exergy generation rate is given sigma dot
Entropy generation.
Entropy generation, right? Okay.
Yes.
Now next question. A steady state counterflow heat exchanger operates adiabatically with respect to surrounding. Okay. And involves no work transfer. So this heat exchanger is adiabatically with respect to surrounding. Okay. Because if we are saying heat exchanger, then there should be heat exchange, and if it is adiabatic, then how heat exchange will take place? So it is actually adiabatic with respect to surrounding. Okay. So whatever fluids are there, they are exchanging heat between themselves, but heat is not being lost to the environment, right? So we have to write the simplified exergy rate balance equation for this particular device, and we have to show that the rate of exergy destruction is related to the change in flow exergy of hot and cold streams. So how will we proceed? Exergy rate balance equation we have to write.
And steady state exergy balance should be equal to 0.
Equal to
0.
We have already written this exergy balance equation somewhere, right? What
Yes,
we
sir.
had written?
Yeah.
Okay, I don't know, something we had written. Okay, this is what we had written. So simply this thing only. Exergy associated with heat, how much it will be? We just wrote 1 minus
T
T naught by Tj, and heat transfer Qj. Okay, this heat transfer is with respect to environment. Okay, minus entropy associated with work, that will be W. Okay, plus if there is some mass coming in, then maybe some mass times exergy associated with the mass which is coming through inlet, minus entropy going outside with the mass. Okay, so mass coming through inlet, Mi, and mass going through outlet, let us say M exit, Me, and associated entropy will be exit. Okay, sorry. This should be equal to what? Exergy destruction, right?
P2 minus ED.
Or you can simply put minus ED is equal to 0. Now it is saying that it is adiabatic with respect to environment. So this heat loss term will be 0. Right? It involves no work transfer, so this W naught will be 0. Okay. So what we have? We have only, we are left with this term. Right? Okay.
Yes.
Okay. Now coming to the next question. A superheated water vapor undergoes controlled expansion through a throttle valve from 30 bar at 320 degrees Celsius to 5 bar. The inlet entropy is given 6.62 kilojoule per kg Kelvin, and the exit entropy is also given. Assuming an ambient temperature of T0 is equal to 293 Kelvin, and that the process is adiabatic. Okay. So expansion means it is going through throttle valve, and it is adiabatic. Determine the exergy destruction per unit mass in these units. Okay. So it is adiabatic, but not isentropic. Right? So this means it is irreversible. Correct? If it was adiabatic isentropic, then it would have been reversible. It is not isentropic because there is entropy change from S1. It has changed to S2. Okay. So it is irreversible. So there will be some entropy generation. Right? And if entropy generation is there, then there will be exergy destruction. So how can we calculate? Hello?
Yes, sir. T0 in delta S TS is equal to
T0 into delta S.
the generated entropy S2 minus S1
S2 minus S1.
into T0 to T0.
Bus S2 minus S1 times T0. We have discussed, no?
Expansion. Yes, sir.
So, and exergy destruction will be entropy
Mass.
generation times T0.
Yes, sir.
Now, what will be the entropy generation?
It's S2 minus S1, no? It is directly S2 minus S1.
Yes, for this case, it is S2 minus S1, but it is not always S2 minus S1 because entropy can change because of some, process as well. Okay. But here it is given, what is given?
Adiabatic.
Yes,
Adiabatic. It is given what? Adiabatic.
There is no entropy
Right.
generation due
So
to the
entropy, okay,
heat-
let me write.
heat
Okay.
transfer. Yes,
Right.
sir.
So entropy change, that is S2 minus S1, that is what? Entropy associated with heat. Okay. So, I mean, del Q by T plus entropy generation.
Delta.
Okay.
Yes, sir.
Okay. Like that. Okay. So if the temperature are small, then we need to replace this thing by D, and all that. Okay. So I will write ds is equal to, anyways. But this dq is 0 because it is adiabatic.
Adequate. So it is
Is
entire
given.
entropy
So,
changes generated.
yes. So entropy generated is whatever entropy is generated as gen, this will be S2 minus S1. And S2 is given, S1 is given, so you can calculate S2 by S1, S2 minus S1, and you can calculate this thing, right? This will be T naught S2 minus S1, okay, per unit mass.
Yes.
Fine.
Yes.
If this was not adiabatic, then what should we have done? We should have
S2 minus S1
calculated
minus dq by t.
exactly. Okay, and whatever the process is, according to that, we would have used this relation for temperature. Okay, and also we discussed that if
Yes.
you know the final state and the initial state, then we can calculate this entropy change. This basically this term, this term. Right? You remember what I'm saying, or I think I should repeat it, right?
No, sir.
Okay.
I got it. We got it. Yes.
Okay. Actually, if we have any 2 points, 1 point, 2 point,
Mhm.
and you have any path, we don't know what this path is, then we simply make two, we make this path,
Two
decompose this path
processes.
in two parts, two processes. One is isothermal, another is adiabatic. So along the adiabatic part, it will 0, and along the isothermal part, we can calculate, right?
Yes, sir.
Okay.
Sir, in the
So
previous problem,
in this problem,
no, just back that heat exchanger problem.
Mhm.
Yeah. Here we are considering the total cold fluid as well as hot fluid as the system. Suppose I am considering cold fluid alone as the system, and question is like that. Then heat exchange is to be taken, no, in the same, even though it is saying it is insulated.
then it will be exergy change of cold fluid only. Okay, if you are considering cold fluid only, then it exergy change of cold fluid only. And if you are considering hot fluid only, then it will be exergy of hot fluid only. And the exergy change of hot fluid will not be same as exergy change of cold fluid. Okay, and that difference will be exactly your exergy destruction. Okay, when we do only for energy, only heat, so whatever heat is lost from the hot fluid, that is exactly equal to the heat that is received by the cold fluid. Okay, but the exergy which is lost from the hot fluid, that will not be exactly same as the exergy received by the cold fluid. Okay, so there will be some difference. Okay, then that difference will be your exergy destruction. But yes, you can consider only cold fluid, you can consider only hot fluid. Okay, but the difference will be the exergy destruction.
Yeah. So in that case, heat transfer is to be considered, right?
In that case, yes. In that case, you will have to consider.
Yeah. Then one more question in this question, question number 20.
The question
We
number
are
20.
saying, yeah, we are saying uncontrolled expansion. That is an isenthalpic process, I think. So why we are telling it is uncontrolled expansion?
Can you please repeat, Aisan?
We are telling uncontrolled expansion in this question number 20. Yeah.
Okay.
So why we are saying it is uncontrolled expansion, or simply
Okay, simply call it expansion. I mean, even if it is control, uncontrolled, we don't care. Okay.
okay, for
I don't
this
know what this
question it is not
uncontrolled means. This
yeah.
uncontrolled is not used for solving the problem. It is just given in the question. Even if it was controlled, this particular information is not used. Okay. Even if it was controlled, we could have proceed in the exactly same way, right? And you are right. It can be considered then it is isenthalpic process. Now question number 21. It is saying that this second law efficiency or exergetic efficiency for a compressor is given by the ratio of, we have several options. Exergetic efficiency is given by which of these expression?
Option D.
Option
D.
Oh, okay, let us see all these options one by one. Exergetic efficiency of a compressor. So for compressor, EF2 is the exergy at outlet and EF1 is the exergy at inlet, and W is the work provided to the compressor. Okay, fine. And we are providing the work to the compressor. So basically, we are increasing the exergy of the compressor. Okay. And we have discussed that exergy associated with the heat has some factor, Carnot factor, but the exergy associated with the work input does not have any factor. Okay. So work itself is the exergy. So the exergy increase for this particular case, for this compressor, should be equal to the work that is supplied to the compressor, because work itself is the form of exergy. But if there is any reversibility associated, then the whole amount of work will not be equal to the exergy increase, right? So the exergy increase is actually EF2 minus EF1, okay? And the work that you are providing, that is W, right? So the actual amount of increase in exergy divided by the work that you are providing. Per unit mass we are writing. So, okay, per unit mass and work you are giving from the outside. So negative sign, fine, okay. So this is the efficiency of the compressor. So yes, first option is correct one. And other options you said D, that those also we should check. Option B, it is not correct, right? Because whenever we are writing any efficiency, what we write what we want, right? Actually, I mean, what we are getting and at what cost we are getting. Okay. So what we are getting in this particular case, we are getting the increase in exergy. At what cost? At the cost of work provided. Okay. So work term should be in the denominator. But in option B, work is in the numerator. So it is not correct. And of course, it is just reciprocal of the option A, and option A is correct. We have just discussed. Okay. Now coming to the next question. Again, it is about exergetic efficiency. Provides a sharper picture of a system's true thermodynamic performance than the first law efficiency, because it explicitly accounts for the quality, work potential of energy being transferred. So it seems correct, right? This is true, no?
Yes, sir.
Yes.
Now, question number 23. It is saying for a closed system receiving heat Q0 S at source TS and delivering heat Q dot U at a utilization temperature TU, the exergetic efficiency is related to the energy efficiency by this formula. Hello? So it is receiving
TS minus TU.
heat. It is receiving heat at TS. Okay, so this is like our high temperature thermal reservoir, right?
Yes.
And it is rejecting at TU. So this is like low temperature thermal reservoir, and T naught is dead state. So if it was rejecting directly to the dead state, then how much work we could have got? We could have got 1 minus T naught
Not by TS.
by TS, right? This is W max, or but
Yes.
W in this case, W actual that we are getting, how much we are getting? We are getting 1 minus
T naught. Which
we are getting this thing where we are rejecting TU by TS. Okay, so the exergetic efficiency, this will be 1 minus T naught by TS divided by 1 minus TU by TS. And energy efficiency, neta, that we have already discussed, that is 1 minus TU by, sorry, यही होता है ना? What is that efficiency? 1 minus TU by TS, right?
Yes, yes, sir.
Okay, so this is our neta.
Yeah.
It is saying that epsilon is equal to neta times what? So if there is something, let us say here it is x, so we have to calculate x, that x will be equal to this epsilon divided by neta. Okay, so this epsilon, that is 1 minus T naught by hello,
Yes, sir.
minus TU by TS divided by this neta, which is 1 minus TU by TS. So we are getting this T naught by TS. Is it correct? Or we are missing something?
There seems some inconsistencies there, sir.
There is some
Sir,
inconsistency.
yeah, I know. If sir, is it work actual?
Actual, by the what could be the possible, right? Maximum.
Yeah, this
Is
will be
it
the
one
maximum,
minus-
right? Instead of rejecting it to TU,
Yeah,
we
that is
can
correct,
reject it.
sir.
Next
Epsilon.
time, work actual.
It's-
Is it 1 minus T0 by TU?
T0 by TU where?
I know whether work actual, is it the work potential at the rejection point? Is it 1 minus T0 by TU? Whether we have to take like that or?
So you mean here it should be like this epsilon like that?
Minus TU by TS.
Okay, I think here it should be reciprocal, no?
Yes,
W
sir.
actual divided by W max. So
Yes, sir. That's what I was also asking.
sorry.
Yeah.
Okay, so now if we divide it, then what will happen?
No, it is correct. This is eta into
It should be epsilon by neta and 1 minus tu by ts divided by 1 minus t naught by ts and whole thing divided by 1 minus
1 minus tu by ts.
u by ts. So this tu by ts will cancel out, right? This term will cancel out and you will be left with 1 minus, you will be left with x is equal to 1 divided by 1 minus t naught by t ts, right?
Ts.
So this will be actually ts divided by ts minus
Yes, minus t naught.
t naught. Okay. But answer that I had is actually it is given x is equal to 1 minus t naught by ts divided by 1 minus t naught by tu. So is it same or different? We can quickly check it. So this will be ts
Ts minus t naught by tu minus t naught by tu. It's not same.
not same, no?
Not same.
Not same. So again, we'll have to check this as well. Maybe we have correct one and whatever given in the answer sheet that may be wrong, but maybe we are also missing something. Okay, so we will have to also check this question.
This question was there in the lecture also, I think.
Okay.
In the previous lecture, so there it was given like efficiency was defined as exergy output by exergy input.
Okay, then maybe we are using the different definition, right?
Yeah, then if you take exergy output, it will be 1 minus T0 by Tu. And if you take the exergy input into Qu, divided by 1 minus T0 by Ts into Qs. And there Qu by Qs was defined as efficiency. Right? So that is how that answer may be coming, sir. So
Okay,
there it was given that.
okay. In the last lecture, huh?
Yeah, in the last lecture, yeah, means yeah. In the video lecture, I also had some doubts in that, but it was derived like that.
Okay, then I will check in the lecture. Then we will discuss in detail in the next session.
Okay, sir.
So we will check this in the lecture. Okay, I will check. And which lecture? Last lecture you were saying, right?
Yeah, in one of the last 3 lectures, whatever uploaded
Okay.
last week.
Okay. Okay, so I will check and we will discuss in the next session this thing. Okay. And what else we had to check? Okay, this only. Okay. Maybe they might have used some other definition and we are using some other definition, right? Now question number 24. The wall of an industrial drying oven has an inner surface temperature at 570 Kelvin and outer surface at 305 Kelvin. Environment is at 290 Kelvin. Heat transfers outward through the wall at constant steady state rate. Explain thermodynamically why the rate of exergy transfer evaluated at inner wall will be significantly higher than the rate of exergy transfer evaluated at outer wall. And what would happen to the difference? So we can calculate the exergy at inner wall and exergy at outer wall, right? So at inner wall, exergy will be how much? Whatever heat is being transferred. So let us say some heat is being transferred. Let us say Q. Okay. So Q
Into 1 minus
1 minus T naught, whatever is T naught is T naught is 295 divided by 570, and at outer wall this will become 1 minus 305 by 5, sorry, 295 by 305. So basically this thing, that is exergy at inner wall, and this is exergy at outer wall. So if you calculate, then exergy at inner wall, this will be greater than exergy at outer wall, right? Right?
Yes.
So and what happens to this difference? This is exergy destroyed, right?
Yes, sir.
Okay. So actually heat which was at higher temperature, that has higher potential to do work with respect to, environment, and the heat which has coming at outer wall, that is at lower temperature as compared to the inner temperature. So grade has been reduced, right? It has just degraded. Okay. Now question number 25, it is saying, referring to the drying oven problem in the previous question, the heat transfer rate per unit area is calculated as 0.2 kilowatt per meter square. We have to calculate the rate of exergy transfer per unit area at inner wall and at outer wall. Subsequently, we have to determine the rate of exergy destruction. So that we have already done now. Right?
Yes,
This is
sir.
what we have done in the previous question. What was in the previous question? It was asking why it is so, right? So it is so because there is this Carnot factor. So Carnot factor is different at inner wall and at the outer wall, right? And why the exergy is being destroyed, and why the exergy is being destroyed? Because of irreversibilities. And why the irreversibilities? Because heat transfer is taking place through the finite temperature difference, right? Finite temperature difference. So this means irreversibilities. So this means exergy destruction. And we can calculate this, right? The difference, right? So we can move to the next question. Question number 26, it is saying, which of the following statement about the exergy destruction is accurate? It is saying that exergy destruction is a thermodynamic property. So is it correct?
No.
No, it is not correct, because exergy destruction is associated with irreversibility, right?
Yes, sir.
And
Yes, sir.
irreversibility is associated with the path. Irreversibility is not a path function. Sorry, irreversibility is associated with the path. It is not the point function. Option B is saying exergy destruction is 0 for any adiabatic process. It is not right, right? Adiabatic process means there is no heat transfer, but irreversibilities can be there. Option C is saying exergy destruction is always a positive quantity when internal irreversibilities are present. So this is right. If the internal irreversibilities are there, then it will be a positive quantity. Exergy destruction will be positive. Last option says that exergy destruction can be negative if the system cools down spontaneously. Exergy destruction is never negative. So again, option D is not right. Okay. Now move to the next question, 27. again true false. It is saying that exergy destruction accounting analysis of a steady flow device, the exergy of power output W is fully available, meaning its exergy value is equal to its internal value. So option 27, it is saying that exergy of power output, exergy associated with work.
Yes.
This is true, right?
Okay.
Exergy associated with work is equal to the work itself. There is no factor like Carnot factor for the heat.
So is it like in exergy? Just a doubt. Because for work, work is a high grade energy interaction. And here, since all the work can be converted like from the portion of potential available, the whatever potential available for work transfer, since it is fully achievable, the entire exergy value for that part will be equal to the work done. Is it like this?
Yes, the work, like we discussed that exergy associated with heat, exergy associated with work. So exergy associated with work is equal to work itself. Okay.
Yes.
So even if the whole work is not, converted from one form to another form, there can be exergy destruction, but exergy associated with work is work itself. Huh?
Yes, sir. I think no. So can you repeat? Can you ask again?
Yeah, but the second
Right.
second
Okay. What I meant is that work can be of different forms, right? Like we don't discuss a different form of work. We consider all the work to be equivalent. For example, there can be soft work. Okay. So if this shaft is rotating, okay, so this is soft work. If the shaft is rotating, but associated with the shaft, there is some, it is raising a weight. Okay. So weight raising is again another form of work. Okay. So if a shaft is rotating and it is, lifting the weight, then the shaft work is somehow is being converted to the potential energy of this weight, and this potential of energy of weight, you can think like work. Okay. So there can be some losses. Okay, there can be some losses. So the actual shaft work and the potential energy increase of this weight, they may not be same. Okay, and the difference will be equal to the exergy destruction, but exergy associated with the shaft work is equal to the shaft work, and exergy associated with this raising weight is equal to uh, the increase in potential energy. Maybe another example we can take from like engine, right? In engine we have some energy at piston, right? And that piston is connected to your crankshaft, right? You are getting some work at the piston, right? That we call indicated power. Okay, so some power we are getting at piston, that is indicated power, and the power we are getting at shaft, that is our mechanical shaft power, or whatever you want to call that. So the exergy associated with this piston power, that is equal to the power of piston itself, and exergy that we are getting at the shaft, that is equal to the power that we are getting at the shaft. Okay, they may not be same, there will be some difference. Okay, and that difference will be equal to the exergy loss. But when we say exergy of power output, exergy of power output is equal to whatever power is being produced at the piston. Okay. Right.
Yes, sir.
Maybe this is not fully relatable to this example because this is open system, but you got the point what I mean, right?
Yes, sir. Yes, sir.
Sir, one doubt. Am I audible?
Yes, you are audible.
So the second portion is saying, meaning its exergy value is equal to its energy value. But whether some exergy distraction also will be there, no? So energy value, whether it will be, can we in general
Magnitude
way
of
can
work.
we
Let
say
us replace equal to the magnitude. Its magnitude. Let us say. Okay. Now it is correct.
yeah, no, it is okay.
The exergy of power output W is fully available. So don't worry about the language. The concept is important. So language, maybe some different, but what message we want to get from this question is that the exergy associated with work power output is equal to the magnitude of that work power output. Okay.
Yes, sir.
Okay. Now question 28. It says for a counterflow heat exchanger without mixing, the exergetic efficiency is defined as the ratio of increase in flow exergy of some stream to the decrease in flow exergy of another stream. So there are two streams, cold stream and hot stream. So as we discussed in the previous question, you are asking that we could have considered only one stream, cold stream or hot stream, right? And we discussed that there will be exergy reduction for the hot stream and increase in the exergy of cold stream. Okay, but that increase in the exergy of cold stream will not be same as decrease in exergy of hot stream, and that difference will be your exergy destruction, and the ratio of increase in exergy of cold stream to the decrease in exergy of hot stream, that will be the exergetic efficiency. Okay. Now we have few more questions. Question number 29. Compare energy accounting and exergy accounting for a system. So accounting basically means balancing. Okay. Energy balancing and exergy balancing. If a heat engine rejects a large quantity of thermal energy at exactly the dead state temperature, explain why this represents a massive energy loss but zero exergy loss.
Exactly at the dead state temperature.
Okay, so
Yeah, no,
energy.
okay. Yeah, no work is done. No, that is why energy is lost.
No, work may be done. Work is being done. Fine. Heat engine is doing some work. Like we have some heat engine and it is rejecting heat at the temperature of dead state. So we can calculate the energy loss. What will be the energy loss? Energy loss will be exactly equal to the energy rejected, right? Energy loss for the system will be equal to whatever energy is being rejected to this dead state, right?
QL.
Okay, because TL is T naught. Okay, but exergy loss, what will be the exergy loss?
Dead state 1 minus.
Yes, exergy at source. What will be the exergy at source? This will be equal to QL 1 minus TH by TH by T, sorry, T naught by TH, right?
Yes,
and exergy
TL
at sink will be
QL
QL times 1 minus T naught by TL, and TL and T naught are same. So this will be 0. Okay. So what is exergy loss?
Yeah, it is 0. Exergy loss is 0.
0.
Exergy loss is 0.
Exergy loss is 0.
Yeah.
Right?
Yes.
Because this is exergy at source and this is exergy at sink. So, sorry. This is exergy at sink and this is equal to exergy loss actually, right? So exergy loss means whatever exergy is being lost at sink, and at sink we are not losing any exergy because it is already at dead state, right?
Yes, sir. Energy at sink is almost
Whatever exergy it had at source, all that amount of exergy has been converted into work, right?
yes,
Because
sir.
work
Efficiency
output
is
will
done.
also be equal to Q times 1 minus
Yeah.
T naught by TH. Okay.
Sir, but we are saying energy loss. Is it because we are not rejecting to absolute 0? One more part is there in the question.
In question, where is the another part? See, when we are saying loss, so loss basically means what we are rejecting to the sink, because once we have rejected to the sink, we are not utilizing that part, right? So energy that we have rejected to the sink, that is equal to energy lost, right? Okay. And energy lost will be not this much. Okay. Here it will not be QL. I have written this wrong. This will be energy loss will be QH minus W. Okay. Right. And W will be equal to your W will be equal to QH1 minus T naught by TH. Okay, this will be your W. So there will be some amount that we are losing, and that amount you can calculate. That will be QL, right? You will be rejecting some amount of energy to the sink. Okay, so QL is not equal to 0. But exergy that we are rejecting at source, that is your exergy lost, right? And we are not rejecting any exergy at source because exergy at sink is 0. We are not rejecting any exergy at sink because exergy at sink is equal to 0. We should write this again because we have just mixed TH, TL, sorry, QL and QS. We have taken some energy from source, QH. Okay, so energy loss is equal to energy rejected at sink, that will be equal to QH minus W, right? Or also you can write QH by TH equal to QL by TL, right? So QL will be equal to QH times TL by TH, that will also be equal to QH times T naught by TH. This is your QL. Okay. But exergy at sink will be energy at sink, QL times 1 minus QL Q naught by QL, and both of them are same. This will be 0. Okay. So exergy loss is equal to 0, but energy loss is equal to QH times T naught by TH. Okay, now it is correct, right?
Yes, sir. Okay. So I was trying to say, like, if T0 was absolute 0, then energy loss will be 0.
Then we will get 100% efficiency, right?
Yes.
100% efficiency means no energy loss. Okay. Question number 30, it says compressed air enters a steady state counterflow heat exchanger. The net change in flow exergy for the cold stream is calculated as increase of this amount. The hot gas stream provides the heat, experiencing a net decrease in flow exergy of this amount. Assuming no boundary work or heat loss to the surrounding, we have to calculate the exergy restriction, and that will be the difference of these two values, right? Okay, so this will be the just difference of these two values, 34.95 minus 12.86 megawatt. Okay. Okay, so this was the last question, and I will check this question. Some ratio wala question tha na koi, this question in the lecture, and that we will discuss in the next lecture. Okay.
Sure, sir.
Rest everything is clear, I think. Okay, so I think we can now stop, and we will meet in the next session.
Yes, sir. Thank you, sir.
Okay, thank you for attending. Good night.